of the review starts to talk about rational solutions. So what we need to remember here, I'm going to say recall, is that a rational number to begin with is specifically any number that you can write as a fraction. Using a regular integer on top and bottom. In other words, given the situation that you have decimals, the rational numbers will only include decimals that either terminate, end, or repeat. Otherwise, decimals that don't follow these rules cannot be written as a fraction with regular integer numbers on top and bottom, so those would not be rational. So the first thing we look at with number 12 is what are the possible rational combinations that would come from this. And something that we saw briefly in this chapter is that we can figure out every single option or every single possible zero in this case by taking these two numbers, the very last number and the leading coefficient, and by taking the factors of these two. So I'm going to say the factors of 18 over every possible combination of the factors of -3. And when I make those into fractions, that's going to be all of my options that are possible coming from this polynomial that would satisfy the rational solutions requirement. So doing that, the first thing I want to know is what are the factors of 18. So let's list them out. Let's see, I have 1 times 18, 2 times 9, 3 times 6. Let's see, 4 doesn't go in evenly, neither does 5. So that's all of the factors of 18. Factors of 3 include 1 and 3, since it's a prime number. So the idea is that I'm going to make combinations with each of these numbers on top of that 1 first, and then with each of these numbers on top of that 3. So the first one's actually easy. If I put each number on top of 1, I'm getting, let's see, 1 over 1, that's a plus or minus 1, because we're always including positive and negative options here. Then we have 2 over 1, so plus or minus 2. And we'll keep going across with the same idea. Plus or minus 3, plus or minus 6, plus or minus 9, plus or minus 18. And then we get to the next number, so 1 over 3. Plus or minus 1/3, plus or minus 2/3. And then let's see, 3 over 3 is 1, we already have that, so we don't have to rewrite it. 6 over 3, that's a 2, we already have that. 9 over 3 is 3, we already have it. 18 over 3, that's 6, we've already got it. So that's all of our possible rational solutions. Now this doesn't just say possible though, does it? It actually says to find the rational solutions. So usually what our strategy is to figure out what the options are, and then we want to look in our calculator to figure out if we have one using the picture. And the case is that usually if we have one, we'll try to extract it using division and keep trying to take out more and more using that synthetic division process that we have to get every single possible solution. So looking at the graph of this is actually kind of tricky. This particular problem is quite tricky in my opinion. I've put in the graph the function that we have that we're looking at, and actually this is a standard viewing screen here. You can see that our degree 4 function is only crossing the x-axis twice, which we know that's reasonable behavior depending on how it flattens out and such at certain points. So when we're looking at this, these 2 points are where we see intersections. Now, I actually spent a while before I came to this conclusion to verify this by zooming in, zooming out, using the zoom fit, and also looking at the table. So I did not just say, hey, look, this is the answer, let's move on. I point that out because when you all are on a test, you don't want to just take the first picture you have. You want to do things like zooming out to see what kind of behavior you see in your function. That's usually the first thing I do past zoom standard. Beyond that, the next thing I would do, excuse me, the next thing I would do is go into your window, play with the min and max values, and then hit zoom fit. So here I'll say, I don't know, negative 200. I've been playing with it for a while. That may not be big enough though. And 200. I can't remember now, but the point is, this is how you get pictures to find out how many times it's crossing. And 0 is zoom fit if you guys have forgotten. On this, we get something similar to what we saw before. It's a little harder to see, so you may need to use your trace button to observe things like, are my y's positive, are they negative, what's the trend here? But the idea is you do want to check your picture on several different zoom levels. Also, what I did as I was looking at this is I actually zoomed out and used the zoom box that we've seen, I believe, once in class, which is kind of like an Etch-a-Sketch where you can zoom into a certain area. So I encourage you guys to be playing with your calculators in this way to make sure that you're comfortable looking at the same graph from different perspective points. Regardless, though, what we end up finding out after lots of zooming is that there's 2 places that this thing crosses the x-axis. To get those places, we hit second calc, 0. Now the interesting thing with this particular one is that the answers we get, the 2 zeros we get, are actually not rational numbers. We end up getting x equals negative 0.7912878 and x equals 3.7912878. I point this out because of the fact that these are not valid. They are valid solutions, but based on this question, it's wanting rational solutions only. Using the picture, we discover that none of these work. Now let me give you all more insight. To look even further into this, I actually took these values and specifically looked in the table for these just to make sure that none of them were giving me the output of 0, because that, of course, the output of 0 coming from any of these x values would have made it a valid rational solution. So we got decimal points, nothing rational, and by testing every one that we knew was a possibility to begin with, we're getting that none of those work. So the answer for number 12 would be none. There's no rational solutions to this equation. There are regular solutions, and if you're on the test, you're welcome to give me the decimal solutions in that case and to circle those. But as far as rational goes, technically there's none. You can just say what the x values were if you want, and I'll round those, I guess, just so you'll have them in your notes. Okay, let's move on then to number 13. I think it's a little more fun because we actually get a good answer that's a little more easy to deal with. It's the same concept, though, on number 13. We have a polynomial here where powers are going from the highest power down. So we're going to take our 27 and our leading term's coefficient 3 and make a ratio between the factors. So we're going to take the factors of 27 divided by the factors of 3. And again, this method is a way for me to figure out every possible rational, in other words, kind of regular number that can come out of these things. And the purpose would have been us trying to find zeros, trying to factor by hand, remember. That's kind of where we were going with this, especially back before we had technology. So let's see. The first thing I'm going to do is say factors of 27. So we have 1 times 27, 3 times 9, 4 doesn't go in, 5, 6, 7, 8. I think that's all of them. For 3, we just have 1 and 3. Nice. So they made that one pretty easy again. Okay, so the idea is, first I have every number over 1. So my options will be plus or minus, let's see, 1, plus or minus 3, plus or minus 9, plus or minus 27. Because again, every single one was going over that 1 as the denominator. Now that I've dealt with the 1, let's look at the 3. Oh, excuse me, the 3 on the bottom. So I have 1 over 3, plus or minus 1/3. 3 over 3, that's a 1. 9 over 3, that's a 3. Again, those are already up there. And 27 over 3, that's a 9. So that's all of the options here. So the idea is to find the one that matches. So by hand. Something we can notice here is that we have 4 terms. That always makes us happy when we're trying to factor. And again, just a reminder to you guys, we know that factoring would be one mode that we would look at first, because we have x's to different powers and we're being asked to solve. So we know we cannot isolate x. Strategy number 2 is, can we somehow get them into pieces by factoring? So I'm going to pair them in 2's. Looking at the first 2 that I have, I'm going to pull out x squared as my greatest common factor. X squared times x plus 7 is what I have. Then ignoring this, the biggest thing that I can pull out will be minus 5. A negative 5 times x gives me the first piece back, and a negative 5 times a positive 7 gives me the second piece. So it looks like that's going to factor pretty nice. So we're getting x squared minus 5 and x plus 7 equals 0. So in other words, we can split this. We have x squared minus 5 equals 0, and we have x plus 7 equals 0. So adding 5 to both sides, we have x squared is equal to 5. To get rid of that squared, we're going to square root it, plus or minus on both sides. So x is equal to positive and negative square root of 5. And over here, subtracting 7 from both sides, x is equal to negative 7. And again, anytime you're playing with stuff like this, different powers, especially even ones, I recommend that you check it. So what I'm going to do is I'm going to type this function in to my calculator and just take a look and see if I'm getting the solutions that I expected from solving by hand. And of course, it's easy to check a square root of 5 in the calculator now that I've got the exact answer. I can match the decimal to just verify my work, to check myself. So again, there's always a graphical connection to this algebra that we're doing. And when you look at it, even on an ugly zoom, you can see 3 solutions. So without even spending too much more time, I got 3 solutions. We're looking pretty good. Okay. For the next one we have, let's approach it pretty similarly. I'll do 2 by 2 since we have 4 pieces. So here I pull out an x squared from the first 2 pieces, ignoring those 2. So x squared times x plus 8. Then for the next 2, I'll pull out a positive 9. And then let's see, 9 times x plus 9 times 8 will give me my 72 back, equals 0. So x squared plus 9 and x plus 8 equals 0. Okay, so here we have x squared plus 9 is equal to 0, and x plus 8 is equal to 0. Solving for x squared over here, I get x squared is equal to negative 9. Now remember, I can't do difference. I can't factor that piece, the x squared minus 9, because that's not the difference of perfect squares. There's a plus in between. So I have to move the negative 9 over and then do the square root. So here I get x is equal to plus or minus I square root of I. 9, excuse me. Which is the same thing as plus or minus 3i. Those would not show up on the graph, remember, because they are imaginary solutions. And then this 8 right here, we're getting x equals negative 8. So we have x is equal to plus or minus 3i, and x is equal to negative 8 on 15.